Nisha. I don't know. Sorry, Nisha. Sorry. You guys sit together now always. What's your name? So you moved into a new house. Okay. All right. So we'll finish this with quadratic programming. Just wanted to give you a flavor of it again, like duality was a flavor. I didn't want to finish without telling you about this. So the standard form, what is a quadratic program? As you would have guessed, a quadratic program would be where everything seems quadratic, means x1, x square, x1, x2, so and so forth, right? But the standard form of it says that the objective function is quadratic and the constraints are linear. So I mean, these can be quadratic as well. So then it will still be called as a quadratic program. But where the objective function is quadratic and constraints are linear is the standard form. So if I have to say standard, this is the standard form of the quadratic program. And if you notice, we have changed the notation here. We are just referring to both the equality and inequality with AI and BI. Except that here it's equal to 0, here it's greater than equal to 0. So usually the Q is symmetric. When you given the standard program, quadratic program, the Q is symmetric. If it is positive semi-definite as well, then it's called as a convex QP. Why will it be a convex QP? Yeah, because what's the Hessian of this? It's Q, and the Hessian of a function is positive semi-definite, then the function is convex. It's a definition, goes both direction. These are linear, which means they are convex and concave both. So we'll say this is convex, this is convex, this is concave, hence it's a convex QP. Everybody okay? Right. So now there are many methods to solve this, and some of you in your projects are using it. In fact, I was saying use that active set methods, interior point method, ellipsoid method, cutting plane method. Cutting plane is also used to solve discrete LPs as well. So those who are doing projects on that could work on those. So if this is a problem given to you, 2x1 plus 3x2 plus 4x1, this, and these are the constraints, you have to write this in the standard form. So to write in the standard form, what will you need to do? You have to find the Q and you have to find the D. You have to find the AIs, and that is of course obvious. So what will we do? How will we do? We'll just write it as half of x1, x2. It's a two-dimensional problem. What will be the dimension of Q? 2 cross 2, right? So you can write it as A, B, C, D, or not A, B, C, D, then E, F, G, H, something else, so that doesn't conflict. And x1, x2, and you make it equal to this, and then you solve for your Q. This is your Q. So your Q will turn out to be once you solve for this, your Q will turn out to be 8, 2, 2, 2. And similarly, if you want to find the A and B and so on and so forth, you can use this guy. So there is no equality constraints. In this one, there is only inequality constraints, and you can find those as well. Is that okay? Why do we have to always? We did that in the linear program also, where we did so much of efforts writing any given LP into a linear program, was because the algorithms which you derived, like the simplex which we derived, or the IP which you will derive in your project, or any other, they take input as the standard program. So it's always good idea to convert it to a standard program. I'm just priming you up on the QP. We're going to go to more exciting stuff in a minute. So let's see what we're going to do. So once we started this section with the constraint optimization, then we moved to linear program, now on the QP program. When we did the constraint optimization, we separated the equality and the inequality. So for the equality constraints, they were necessary condition sufficiency. How many necessary conditions did we have for a general constraint optimization problem? 2. What were those? Feasibility condition, ai of x equal to 0 and the Lagrange multiplier, the gradient of the function is linear combination of the constraint, or the gradient of the Lagrangian with respect to x is equal to 0, or you can write the equality constraint as gradient of the Lagrangian with respect to lambda equal to 0, the whole thing, the gradient of the Lagrangian is equal to 0. That is what we did. Then the sufficiency condition we did, how many were there? 3. We added the third condition, which was the Hessian of the Lagrangian with respect to x is positive semi-definite or positive definite over the null space of Jacobian of constraints, correct? When we went to general inequality, how many necessary we had? We had the 5 KKT condition and the 6th condition here, remember? The equality, the inequality, the Lagrange multiplier, the complementarity, the non-negativity, and the last one was the same as here. The great Hessian of the Lagrangian is positive semi-definite over the null space of Jacobian of constraints. Then when we went to LP, how many necessary and sufficient conditions we had? We again had 5. The 6th condition was not playing a role here. The 5 KKT conditions were playing a role. Remember in simplex where mu was bothering, and we just did IP where x and mu both were being made strictly greater than 0. So now similarly for QP you will have the equivalence. What we did was we took these necessary and sufficient condition and simplified and got the sufficiency conditions in the case of LP. The 6th condition was redundant, it was by default satisfied. So similar things we can do for this. So what we'll do is today we'll going to see necessary, what happens to this, and we'll see what happens to the sufficiency. I'm not going to go to the general inequality case, we're going to skip that because there's less time. But I'm going to at least give you a flavor of what happens in the case of equality constraints. Why do we want to do that? Because now we know our problem has a very nice structure. It is of this form and this form. So in that case, those conditions which we wrote, they will become simpler. So we're going to just simplify those conditions today. Is that okay? We've not done anything. This is the linear function, no? There is no. Sorry, this was. I wrote something wrong. This will carry the x transpose d, no? So you will say that d is equal to 2, 3. These quadratic terms will give you the q and the linear terms will give you the d. Is that okay? Alright. So now let's jump to this guy. So we're going to start with this condition, exploit the objective function and the constraints like this, and see what better conditions do we get. Okay, so that is where we're going. Okay, so we're starting with equality constraint QP, and the very first thing is we're going to look at the necessary conditions. To write the necessary conditions, what were the 2 necessary conditions? So I will not write the whole thing, I'll just write the conditions. It says if x star is a minimizer of this and a regular point for the constraints that are active at that point, then these 2 should be true. So the very first thing is that the constraint should be satisfied. AI x star should be equal to bi, or ax star is equal to b. And the second condition was the gradient of, we have to write the Lagrange. You can write it both way. Gradient of the function linear combination of the constraint, of the gradient of the Lagrangian with respect to x is equal to 0. So if I have to write the Lagrangian for this, that would be half of x star transpose q x star plus x star d minus lambda star transpose ax star minus b. Correct? Yes or no? We have done a similar problem when we did constraint optimization, but we are going to see something more nicer today. So we have to say gradient of this is a linear combination of gradient of this, or make the gradient of the Lagrangian. So this is equivalent to saying that the gradient of the Lagrangian with respect to lambda equal to 0. And now we're going to say that the gradient of the Lagrangian with respect to x equal to 0. Correct? Yes or no? So what do we get? Aviral, right? Abhinav. Tell me, Abhinav. So what should I do?
Sir, we can take
What is the gradient of this? Tell me. Qx star, because this is a vector which will come out. Correct? Everybody knows this now. And this would be plus d. Correct? And then we have to do gradient of this. To do that, I will, rather than a gradient of this transpose this, I'll write this transpose this. Then I can see that, like we have done in the case of LP, right? So I can write this as x star transpose A transpose minus B transpose times lambda star. Correct? Now if I take a gradient of this, what will I get, Abhinav?
A transpose lambda square
Minus A transpose lambda star equal to 0. Correct? This kind of a thing we have done as a problem in the constraint. We go to something beyond that. So this is my one equation. This is my second equation. In fact, you had solved this with me when we did one example in the constraint optimization case. Correct? So we are going to solve for this. Or we want to write this. So we'll write this as Qx star minus A transpose lambda star is equal to minus D, and other one is AX star is equal to minus B. So you had to write this, it was Q minus 8 star A 0 X star. Sorry? Equal to plus B, sorry. It's still plus B, so this is lambda star is equal to minus D and B. Okay, so now what is important for us to find one of the candidates for a minimizer? This guy should be what do we have to do to find a solution to this? Yeah, prove that it's invertible, right? If it's invertible, then it has a unique solution and you have a candidate for the minimizer, right? So I'll write a lemma for this. So the most easiest thing to do in this one would be if Q turns out to be positive definite, positive semi-definite in fact, and A is full row rank, which is given to you. In that case, this will turn out to be invertible. We had proven this in the example which we had done earlier. But now we want to relax this condition. So we want that, can we make this slightly more weaker assumption, because finding a Q which is positive definite over all of this Rn space is difficult. So we'll see if we can find some other condition which could still make this invertible and but not be positive semi-definite over all of the space. So the lemma says that if it is positive semi-definite over the null space of, let A be full row rank is Z, and Z is given by the null space of A. So if you can find the null space of the A matrix and prove that this guy is positive semi-definite over that space and this is full row rank, then also it will be invertible. You getting me? So instead of saying that, let's say this is all of the space, the Q is positive semi-definite over all of Rn. If this was defined as Rn, although it's unbounded, we are saying that you take one small space which is the null space of A and show that Q is positive semi-definite over this. So this is a weaker condition, right? This will be more easier to satisfy than satisfying it over all of this space. So that is what the theorem we're going to write now. Is that okay? So the lemma says, this is a lemma rather than a theorem, says let A be full row rank and assume that Z transpose QZ is positive definite, where Z is the null space of A is defining the Z vectors. You write it as. So if A is full row rank and assume that Z transpose QZ is positive definite, where Z is the null space, the basis for the vectors of the null space of A. So So the lemma says if A is full row rank and Z transpose QZ is positive definite, then K, this is your K matrix, this is invertible, and then hence there is a unique solution to this. Now what is Z? The columns, Z is the columns which form the basis of the null space of A. So if it is Z1, Z2, Z3, we are saying Z1, Z2, Z3 span the null space, and Z1, Z2, Z3 are linearly independent. You know, what's the definition of basis? They should be linearly independent and they should span the space. That is how it becomes, you know, a basis vector of any space. Okay. Alright, so we got to prove this now. Is everybody convinced? Why do we are doing this work? If I had to just say this is positive definite, this is full row rank, this we have already proved. So we don't have to worry. We are trying to work towards and relaxing this condition. Correct? Okay. So how will we prove that something is non-singular? What are the characterizations of proving something is non-singular? First is determinant is not equal to 0. No 0 eigenvalue. What is another characterization? If we say A matrix, Ax equal to 0 has a unique solution, x is equal to 0. That's also one of the characterization of a invertible or a non-singular matrix. Okay. So we are going to show that if this is my K matrix and I multiply with vector V and make it equal to 0, this would imply that WV equal to 0. Correct? If I can show this, then I'm done. Everybody agrees? So let's try to work it out. So we'll write the first equation. So it's QW minus A transpose V is equal to 0. Okay. So what we'll do is not this. We'll multiply. So we'll take the left hand side here and multiply with WV transpose on both sides. So what do we get? WV and this is QW minus A transpose V and A times W, and this is equal to 0. And we multiply this, so this transpose, what do we get? W transpose QW minus W transpose A transpose V equal to 0, and we get V transpose AW is equal to 0. We starting with this, है ना? We multiplied both sides with V transpose W, and this is what we got. So what do we get? No, I did something wrong. This into this plus this into this. So this is plus V transpose AW equal to 0. Correct? This is nothing but V transpose A, and this is W. A transpose B and B transpose A. That's what it's written. So these two will cancel out. Correct? So what do we get? We get that W transpose QW is equal to 0.
So is the transpose inside, like it's W transpose, V transpose? Because what you wrote before should be correct if we are writing it like this.
It's this times this plus this times this, huh? So W transpose QW transpose minus W transpose A transpose V plus V transpose AW. Which T? This you're saying? Correct. I mean, I would rather otherwise write this as this. Huh? Okay. So then this becomes this. Now what do we know about W? This is nothing but A transpose B and B transpose A. This could be written as W. They transpose of each other. Na? This is W transpose A transpose V. So they are the same, so they will cancel out. They're scalars, huh? Scalars. So what do we know about W? Okay, do we know anything about W? Sorry? It's in the null space of A. Good. So if you look at the first equation here, we know A times W is equal to 0, which implies W belongs to the null space of A, which implies that W can be written as some Z times U. Z is the matrix whose columns are forming the basis of null space of A. So we are taking the linear combination of that and writing W. Correct? Everybody with me? So we'll substitute this into this. So we get U transpose Z transpose Q Z U is equal to 0. Correct? What do we know about this guy? That it is positive definite. Correct? That is what's in the definition. I've erased it. This guy is positive definite. So nice written. This is positive definite. What's the definition of positive definite? For all U not equal to 0, we have got U transpose Z transpose Q Z U is greater than 0. Correct? This is the definition. What is the negation of this? Transpose Z transpose Q Z U not greater than 0 would implies that U is equal to 0. Yes? Yes or no? So what do we get? This implies U is 0, which would imply W is 0. So at least one part we were able to prove that W is equal to 0. Correct? W is Z, this is 0. So multiply anything with 0, you will get W is equal to 0. Z is the null space of A. So the columns of if Z1, Z2, Z3 are coming from the null space of A, it is the columns are put together. They are basis vector, which means they are linearly independent, and any vector in that null space can be written as a linear combination of them. That's the true definition of a basis of any space. Correct? So we were able to know from this first equation AW is equal to 0 that W lies in the null space of A. We know that this null space is formed by the columns of the Z matrix. So we took a linear combination of them and wrote it as Z. Then we substituted it back into this and we were able to prove that U is equal to 0. Since U is 0, W is 0, so half of the work is done. Correct? Yes or no? Now what do we have to show? We have to show V is also equal to 0, then our work will be completely done. So what do we know from this equation? QW minus A transpose V. So this equation had come from this, है ना? So another way this equation will give us is QW minus A transpose V is equal to 0. So this is equal to 0, we already know, and then we get minus A transpose V is equal to 0. Correct? Yes? So what is, let's say A has A1 transpose, A2 transpose till AR transpose as the row. This transpose V is equal to 0. I've written a transpose on them because I'm writing them as a row vector. Okay. Now if I take the whole transpose of this is A1 through AR till V1 through VR equal to 0. V1 A1 till VR AR is equal to 0. What do we know about A1 through AR? A1 through AR are linearly independent because A is full row rank. Full row rank means the rows are linearly independent. So when you have these set of vectors added equal to 0, they are linearly independent only if V is equal to 0. Everybody okay? Yes or no? Alright, so we proved that if A is full row rank and Z transpose QZ is positive definite, then that KKT matrix is invertible and there is a unique minimizer. You will do one problem in the tutorial today. This is the second problem I am talking about. This is a note. This you already know, but I'm still writing as a note. I'm just trying to tell you this is a stricter condition. This is a more weaker condition because this is making the Q positive definite on a smaller space. This is making Q positive definite over a larger space. So this will always imply this, but the other direction will never be true. Hai? Never means it will be difficult to prove, or because you're going from a smaller space to a larger space. If I have to prove that if Q is positive definite, this is positive definite, how would I prove it? Help me. So there exists some U not equal to 0, or for all U not equal to 0, show U transpose Z transpose Q Z U is greater than 0. Correct? This is what we have to show. So we'll say take, without loss of generality, take any U to be U1 and you write this as U1 transpose Z transpose Q Z U1, and this U1 is not equal to 0. Okay, we'll write this now this. So this can be written as Z of U1 times Q of Z of U1. Correct? ZU1 I am calling this some other vector W1 transpose ZU1 W1. I am also going down in energy. Anyways, so this is W1 transpose Q W1. I am calling this as W1. Now is this positive definite? Is it greater than 0? When W1 is not equal to 0. Hai? So this is greater than 0 if W1 is not equal to 0. So say W1 is equal to 0. So this would imply that ZU1 is equal to 0. But Z contains set of linearly independent vectors, no, Z1, Z2, Z3, because they are the bases of the null space. So this will imply that U1 is equal to 0, so a contradiction. Can everybody see? Okay. So now what you do is, rather than making you do a problem on this, we'll just prove. So now what we show is that the condition which I had written, A is full row rank and Z transpose QZ is positive definite, gives us a unique minimizer, a candidate for minimizer. It is also the minimizer. So the conditions which I wrote earlier, no? So the conditions which was that A is full row rank and Z transpose QZ is positive definite. So it gives us three things. It gives unique candidate for minimizer. This is what we just showed. It gives us a unique candidate for minimizer because we just satisfied the necessary condition, the equality constraints and the gradient of the function. We also show that it is a minimizer. It is not just a candidate, it is a minimizer. So it is a minimizer. What do we have to do? To show that it is a minimizer, Aviral would know. Besides Aviral, anyone? Avira? You come to class, you should remember this. You were able to have your lunch? Okay. अब तुम्हारी प्रैक्टिस ही हो रही है एग्जाम के लिए, just a week away. You should know this, right? What is the sufficiency condition besides Aviral? Sanjana, निशा, आदिति, किसी को याद ही नहीं? अभी तो मैंने बताया था वो इतनी कहानी लिखी थी 2, 3, 4, 5, 6 what all I was writing. Yeah, the Hessian of the Lagrangian is with respect to x is positive definite over the null space of Jacobian of constraints. So now try to satisfy it. What is the null space of Jacobian of constraints? Z itself, because the constraints are, they are only equality constraints, Ax equal to B. If you take the Jacobian of that, it will be A. Null space of A is Z. So you have to just show that the Hessian of the Lagrangian with respect to x is positive definite over Z. You know, nulls, the columns of Z which are forming the space. So now find the Hessian of the Lagrangian with respect to x. What do you get? Karo na, find it. Write the Lagrangian, find its Jacobian, find its Hessian with respect to x. Work it out. Nice, cube. So basically, you had to force that Z transpose QZ is positive definite, which is already given to you. So it automatically satisfies the sufficiency conditions. That's what I'm trying to tell you. But work it out, no? Write the Hessian of the Lagrangian with respect to x. Write the null space of Jacobian of constraints, and then you will be done. So we had just written this, no? X comma lambda is half of x transpose qx plus x transpose d minus lambda transpose ax minus b. Correct? This is what we had written as the Lagrangian, and then we had written the Lagrangian with respect to x was qx plus d minus A transpose lambda. Correct? So now what will be the Hessian? Nothing but Q. So that's done. That's one thing. And then you had to find null space of the Jacobian of constraints. So you had to find the null space of Jacobian of, because your constraints are Ax minus b is equal to 0, the Jacobian of Ax minus b is nothing but the A matrix. So you have to find the null space of A, which is the columns of Z, the Z matrix. So what was the condition? That this guy should be positive definite over the null space of Jacobian of constraints, or if Z is the matrix whose columns are spanning that space, then need Z transpose QZ to be positive definite. Usually we write it with this sign, or we write it positive definite. This is given to you in the problem. So hence the sufficiency conditions are all also automatically satisfied. So once you find it, solve for that unique minimizer, it will not just be a candidate, it will be a minimizer. Everybody okay? Doubt, Misha? Ask me. Okay? Aditi? Clear? If not clear, I'll repeat it. I've just went real quick. I thought you know all this. Doubt hai to pucho. Pucho. You're thinking. Ask me na. So what was the condition? The condition, if you recall, the theorem said, show the sufficiency condition in the equality constraint case was the Hessian of the Lagrangian should be positive definite over the null space of Jacobian of constraint. Or if you find Z to be the matrix whose columns are forming the basis of the null space, Z transpose QZ should be positive definite. So once these are your constraints. Once you find the Jacobian of this, it will turn out to be A. This we had found it. So now what's the null space of A? We already know that the columns of Z are forming the basis of null space of A. This is given to us. So we had to just show that Z transpose QZ is positive definite, which is already given to us. Everybody with me? So now we proved this also below. Now the third thing which is also coming from this little two assumptions which are making things life nicer for you is that it is not just a local minimizer, in fact it is a global minimizer. Because it's a convex problem, so it's a global minimizer. So that is why we study this kind of QPs, because they are nicer. I mean, we could have been lazy and not worry about and say just assume Q to be positive definite, but then in real life you may realize the Q's which you get may not be positive definite, but when you look at this space Z transpose QZ, then they turn out to be positive definite. What will be the dimension of Z transpose QZ? Think about that. Yeah, it will depend on how large is your null space. But there is a theorem which says the rank plus nullity is equal to the total dimension. So it depends on the rank of the matrix in that sense. Is that okay? So it depends on the rank. When we are saying A is full row rank, which the rank is R, and then the total dimension are n, so the nullity will be n minus R in that case. Just think about this. I'll just stop here. This is what I wanted to do. If you want to take a break, take a 5 minutes break. We'll do 3 problems just to emphasize this. The first problem is duality or all is QP. All is QP. So you stop the recording. So then for the quiz is after this, whenever you finish those 3 problems, if you finish early, then you can go and wait.